So hello and welcome also from my side. My name is Arne Jacob. I'm Deputy Team Lead of the Consulting and Projects team at Mass2Market. And today I'm going to show you the newest features regarding upscaling mercury injection or intrusion capillary pressure in an MPL and GDL compound within a fuel cell. So you might have also noticed that this picture has been shown quite often. I have this picture here in my presentation as an overview of on which part we are looking at in this talk here. And that would be the compound of the microporous layer and the GDL on the cathode side of the fuel cell, which would look like this in GeoDict. So just a short overview what capillary pressure or mercury intrusion capillary pressure is actually. So in principle, you have a high contact angle of the mercury versus the air on a certain material. High means usually higher than 90 degrees. That is then non-wetting. So you would have to apply an external force to force mercury inside of the structure. And based on the force you will obtain a capillary pressure curve, which means that you get the saturation of the mercury as a function of the pressure. And why would we like to do that? We will need the capillary forces, or we would need the knowledge of the capillary forces that are knowledge in the fuel cell to get rid of the water that is in the GDL. So as I was shown before, a compound of a GDL-MPL would look like this, where we have on top the gas diffusion layer that is resolved by your microcity or by some structure generator in GeoDict. Then we have a mixture of GDL and MPL, where we have partly resolved parts, the microporous layer and the GDL as well present, and then a homogenized microporous layer on the bottom of the structure. So the question would be here is, how can we obtain the accurate capillary pressure curve across these different scales? We're having the resolved top part of the structure, but we're also having still the unresolved part on the bottom. And the idea is that we would like to combine the information we have from both scales. So this is an upscaling problem here in that case. So first of all, for doing upscaling, we need the function of the capillary pressure curve for the unresolved part of the structure. That can come from experiments where you have solely analyzed the microporous layer, but that can also come from a former GeoDict computation where you have generated a microporous layer, for example, run the capillary pressure command of the GeoDict module, and then you would be able to assign this capillary pressure function to that porous material on this structure, where you can then, by using upscaling, compute the bulk capillary pressure curve. And that would look like this. The mercury first occupies the resolved part of the structure, and when the pressure becomes high enough, it will also start saturating the unresolved parts of the structure, because then the capillary pressure is high enough to also saturate these unresolved structures. The GeoApp, or the application, how it was implemented in GeoDict, is rather simple. You can choose from two options of how you would like to populate your porous material inside the GeoDict structure. The first of all would be that you use the powerful constituent material database in GeoDict and save the pressure and saturation capillary pressure curve directly into the material. So you're having a material, for example, with the name Microporous Layer. And that material can have certain properties like porosity, density, but also the capillary pressure curve as well. So you assign these parameters to that material, and then you would have that graphical user interface in the GeoApp available, where you choose which would be the result file name, from which side the mercury you should invade the structure, and if you upon which saturation you would like your unresolved structure parts to conduct fluids. So there may be a case where you would like to have a microporous layer that does not consist only of one layer of microporous material, but also maybe of two. Let's say you want to have the partly resolved microporous layer with GDL as a material and the homogenized microporous layer as a material. Then you would need a certain saturation which you assign to the upper part of the microporous layer to tell GeoDict upon which saturation that layer should conduct the fluid to the next layer. And that is what you change here in that box. The parallelization is simply how much CPU cores GeoDict will use to perform the computation. The other option would be that you simply load the GDR file that comes out of the GeoDict capillary pressure module. So let's assume you're having you have a microporous layer that was generated in GeoDict. Then you can run the capillary pressure curve command on that structure, which you can then use as an input for this GeoApp to assign the capillary pressure curve to the unresolved material in your structure. And that can be done for up to 3 materials at the moment. The results would look like this. So you would obtain a capillary pressure curve that contains of a resolved part and an unresolved or so-called upscaled part. So in principle, the blue part of the structure consists of the GDL that gets saturated, while the red part consists of the MPL that gets saturated once the pressure reaches a certain level. Based on that, you can, of course, also derive the pore throat diameters of the structure, where you then would have the pore size distribution for the GDL resolved and for the unresolved part also the pore throat diameters. So this is directly copied out from the GeoDict result file of that GeoApp I've shown before. And that can, of course, help you to optimize the MPL and GDL compound, to optimize liquid water removal, or in principle, design better cathode layers here. But what would the GeoApp be without any verification? We have, for the verification, created 2 structures, where we created a structure with a high porosity, or granular structure with high porosity, and one with low porosity. We have now computed on both structure the capillary pressure curve, or Mercury intrusion capillary pressure curve, so that we would have a homogenized material information for, in that structure here, the left-hand side for the high porosity structure, and for the low porosity structure on the right-hand side. So we simply transferred the information we are having from both structures to the left and to the right-hand side. So each of these 2 areas here have one individual capillary pressure curve that can be upscaled directly from only this structure here. And for sanity check, we have also stitched that structure together into a only resolved structure, where we then run the capillary pressure command on. So the idea was, if capillary pressure curves obtained from both of these 2 structures are looking the same, we know that the upscaling approach works. Yeah, because we are having only resolved structure capillary pressure curves and only non-resolved structures. And as you can see, the match is quite well. Yeah, so for the resolved structure, or the blue curve, we are having an almost identical curve as for the upscaled curve. Only here, at that narrow part of saturation above 90% or around 90%, we are having a small deviation that could be also a boundary effect of this structure here. But that is only the first step. The next step would be to not only compute the capillary pressure curve, but to also compute the relative properties that can be derived from certain saturation levels of that microporous layer and of the gas diffusion layer. And that will be possible in the GeoDict 2025 version in one of the next service packs. So in principle, it is very easy. Principle. You having a saturation, and based on the saturation level, you would like to obtain the, let's say, permeabilities, like Jürgen showed you before. Based on a certain water saturation level, you want to obtain the permeability. That can now also be done if there are porous regions involved. So you're having a two-phase flow that is upscaled, so partly saturated MPL and gas diffusion layers. And based on these partly saturated layers, you can then obtain the relative permeability on the basis of different saturation stages of the water. And as shown before in the MICP GeoApp, you can also then use the relative permeability from the unresolved material, and there also from GDR files where you have obtained the relative permeability from the scale below to populate your model on the scale where you have both porous and non-porous materials present. And with that, I would like to close my talk. Thank you.